Hello everyone. So this video is going to be going over a few more examples of the second derivative test to help you understand how we classify critical points as maximum or minimum points using the second derivative. Now let me share my screen. Okay. So what's the second derivative test all about? And what are the steps involved? First, you find f prime and f double prime x. And you find the critical point in the usual way by equating f prime x to 0 and finding the x value at which f prime x is 0. And to get the coordinates of the critical points, the x and y coordinates, you obtain x in this manner. And to get the y value, you plug in this x into f of x into the original function to get the corresponding y value. And so you have your critical points. Now the next step is to classify and understand whether these critical points are referring to a maximum point or a minimum point. And this is where the second derivative comes into play. Now, what you do is you have f double prime x with you. Now, compute f double prime x when the value of x is given by the value is given by the critical point. So you plug in this particular value x star into f double prime x and you compute f double prime of x star. If this expression is negative, then you're dealing with a maximum point. If this expression, if f double prime at x star is positive, then you're talking about a minimum point. Now for the purposes of this video, we'll be focusing only on these two cases. You may ask, what happens if the second derivative is also 0 at the critical point? That is a tricky condition which requires a little bit more attention. So we'll focus on that in a separate video. For now, we'll focus on these two conditions. And we have a summary of the first and second order conditions required for a maximum and the minimum. So the first order is that the first derivative is equal to 0. The second order condition is that for a maximum, you want the second derivative to be negative. For a minimum, you want the second derivative to be positive. And think of each of these using the U-shaped figures that we saw. For a maximum, you're thinking of an inverted U. And for a minimum, you're thinking of it equal traditional U. Let's do a few examples, and that will help us understand these concepts much better. So we're given a function y is equal to minus x squared plus x plus 1. And wait, what am I checking here for? Yeah, great. So we have minus x squared plus x plus 1. And we want to find and classify the stationary points, or in other words, the critical points of this function using the second derivative test. Let's get going. So the first step here is you equate y prime to 0. And you find the corresponding x value. And we see that it is going to be half. Now, when x is half, we can plug in x into the function and see what the y value will be. And that comes to be 5 by 4. Now, half comma 5 by 4 is a critical point of this particular function. Now, is this critical point a maximum or a minimum? Let's go ahead and look at the second derivative. Now, if y is, I'm just rewriting this for ease of reference. This is y, and y prime is minus 2x plus 1. So y double prime is actually just minus 2. And this number is definitely less than 0. And notice what's happening here. The second derivative is negative regardless of the value of x. And that tells me that y is a concave function. Because the second derivative is negative throughout. And I can even confidently tell you that this is a concave function that is shaped like an inverted U. Oops. And how can I tell you this confidently? Well, one is that the second derivative is a negative number and it's not a function of x. And more importantly, the function that's given to me is a parabola. And it is going to have an inverted U shape because you have a minus x squared here. Okay, so if this is a concave function, then what does it tell us about the critical point? Is half comma 5 by 4, is it a maximum or a minimum point? Well, when you see an inverted U, you're going to think that this is a maximum point. Let me put it in a different color here. So you have half comma 5 by 4. Therefore, the particular critical point is a maximum. Now, I showed you the calculus way of doing things. Let's go ahead and see if we can plot this on a graph and verify if our answers are right. So let me quickly stop sharing this screen. And I will now share my graphing calculator. Okay, so I have a bunch of functions here that I'm planning to go over in this video. Let me choose just the first function, which is minus x squared plus x plus 1. And there you go. So this is a proper downward, it's a downward open parabola. And you see how it takes an inverted U shape. And let's zoom in and see where this maximum is actually happening. Remember, our critical points are half comma 5 by 4. Let me scroll up here. There it is. So that's the maximum point. And you see it right there. 0.5 comma 1.25. And that's just half comma 5 by 4. And that is the particular maximum value for this function. Okay, let's do a couple more examples involving just the parabolas. So we have y is equal to x squared minus 4x plus 4. Let's go ahead and classify these critical points. So I have y prime equal to 0, and y prime is actually 2x minus 4, 0. Therefore, x is equal to 2. When x is 2, y is going to be 4 minus 8 plus 4. So I actually get y to be 0. Is that right? Yeah, I have 4 squared, 4 minus 8 is minus 4 plus 4 is 0. Correct. So 2 comma 0 is my critical point. Let's go ahead and look at the second derivative. Oh, I just realized I have not yet been sharing my screen, and my apologies for that. Sincere apologies there. So I have y is equal to x squared minus 4x plus 4. So I equate y prime to 0 and I find x in y, and 2 comma 0 is the critical point. Let's look at y double prime, which means I want to differentiate this particular function, 2x minus 4. My y double prime is just 2, and 2 is always greater than 0 regardless of the value of x. And here we are dealing with a convex function. And in fact, this is a convex function that is actually U-shaped. And I am confident in that because I know I'm talking about a parabola, which is upward open. Because the coefficient of x squared is positive, so it's going to take a U shape. And because my second derivative is also positive, I know that this critical point, 2 comma 0, is a minimum point. Can we go ahead and check that using a graphing calculator? Let's do that. So we're back to Desmos. So I will uncheck the first graph and I will check the second graph. And there you go. So this is a graph of x squared minus 4x plus 4. And you see how it is a proper U-shaped parabola. And the function has a minimum here. And the coordinates are highlighted to be 2 comma 0. So 2 comma 0 is a minimum in this function. Now I will stop sharing this and go back to my workbook. And let's try another example. So we have another U-shaped parabola here. So let's go ahead and classify the critical points of this function. So y prime, we want y prime to be 0 to find the critical points. So this is just 2x minus 20 is 0. Therefore, I know my x is just going to be 10. And when x is 10, what is my y going to be? So y will be 100. minus 200 plus 105. So it's minus 100 plus 105, and y is just equal to 5. Therefore, 10, 5 is my critical point. You must be starting to guess that if this point is a maximum or minimum because of the shape of this parabola. Maybe pause this video for a second, think about the shape of this parabola, maybe plot it out, and then try and get a sense of what 10, 5 is going to be, if it's a maximum or a minimum. Now let's go ahead and compute the second derivative. So the first derivative is just 2x minus 20, and the second derivative is just 2. And 2 is always greater than 0, regardless of the value of x. So the second derivative is positive throughout, and this is a convex function. If it's a convex function, and in fact, this is a U-shaped convex function, and to this particular point, 10, 5 is a minimum. And how do I know it's minimum? Because my second derivative is positive. Let's go ahead and look at a graph of this function as well. So back to this. I will uncheck the earlier graph and open the next one. So this is the graph of the function y is equal to x squared minus 20x plus 105. And you see how this is a proper U-shaped function. And the critical point that we found out was 10, 5. Is that a minimum? Absolutely. You see the parabola takes on a minimum value at 10, 5. So what I will do now is I'll stop sharing my screen and I'll stop my video here. And in the next video, I'll take you through some functions that are not exactly parabolas, and we'll learn how to classify the critical points of those functions. So I will see you in that video.